Welcome to Trigonometry section 4.1 Basic Graphs. So to graph the function y equals sine x, we begin by making a table of values of x and y that satisfy the equation, and then we're going to use the information in the table to sketch the graph. We're only going to make a table this first time, and then after that you're going to memorize some of the key points and features of the graph, so you don't have to make a table every time. So let's start off. We'll select certain values of x from our unit circle, and then y, in this case, is equal to sine of x. Okay, and then we're going to just pick some of the x values that we've memorized from the unit circle. So I'll direct you. We'll do negative pi over 2, negative pi over 4, 0, pi over 6, pi over, let's do pi over 4, then pi over 3, and pi over 2. We might add to it on the fly. And then y equals sine x. So now just imagine your unit circle. Okay, negative pi over 2, that's quadrantial angle, the negative y-axis. So the value of sine there is negative 1. Negative pi over 4 is negative rad 2 over 2. Useful fact to know. Rad 2 is about 1.4. Rad 3 is about 1.7. Both of those come up so much in trig, and it's helpful if you have that in your mind because then you don't need a calculator. So negative rad 2 over 2, think it's about negative 1.4 divided by 2. So that's going to be about negative 0.7. At 0, sine of 0 is 0. Sine of pi over 6, that's a half. Sine of pi over 4 is rad 2 over 2, so that's about 0.7. Sine of pi over 3 is rad 3 over 2. So half of that, half of 1.7, if you round it, is about 0.9. And then sine of pi over 2 is 1. I'm also going to ask you to add a few more right now. We're going to do pi. Sine of pi is, that's correct, 0. And then we will also add the rest of the quadrantial angles. So we'll add in there 3 pi over 2. Sine of 3 pi over 2 is negative 1. And 2 pi, which is 0. Okay, so now let's put everything together. Let's make our graph. This is my y-axis. Always label. Make sure your axes have arrows on the ends of them. There's the x-axis. And later on, when you're going to graph the sine function, you're going to need to include 5 key points. So the key points are going to be at 0, 0. Next one's going to be at pi over 2, 1, pi 0, 3 pi over 2, negative 1, and then 2 pi 0. All the other points we have in the table are just to help us get an idea of what the shape of the graph looks like, but in the future, just those 5 points will do it, okay? So notice they're spaced out pi over 2 apart, and that's all that you need to include for most of your scaling. This graph's going to be exceptionally detailed though. So here's negative pi over 2, then we would put pi over 2 here, pi, here's 3 pi over 2, and then here's 2 pi. But we've added some detail here, right? So we've got negative pi over 4 in here, positive pi over 4. Let me make this a bit thinner so I can really get in there. Then pi over 6, that's going to be a third of the way to pi over 2. So maybe somewhere around here is pi over 6. Here's pi over 3. And that's good enough. Okay, so now let's start making our graph. So at pi over 2, the y value is negative 1. At negative pi over 2, excuse me. At negative pi over 4, it's negative 0.7, maybe somewhere around there. At 0, we have 0. Pi over 6, 1/2. Pi over 4, 0.7. Pi over 3, 0.9. And at pi over 2, sine is 1. I'm just reading it off the table. At pi, we're back to 0. 3 pi over 2, negative 1, and 2 pi 0. Okay, so you can hopefully see that it has this nice shape. Looks like a wave. Okay. Put arrows on the ends of your graph. Make sure too that you're careful with the direction the arrows go in. So notice here at the arrow on the left, okay? Oh, there's nothing worse. I erased too much. This one you don't have to stress about. There's nothing worse than when I see some student draw the graph like this. No, it's not going to go below -1. So don't do that. Don't give that misleading arrow. Make sure you draw it in a way that makes sense. So what's important to observe about this graph? Well, one thing is that it never goes above 1, +1, or below -1. It's bounded between those two values. And then I stopped filling in values after 2 pi because we know we're just going to keep going around the unit circle again and again, and the values of sine are going to repeat. So this graph is just going to keep repeating that same shape over and over. Every 2 pi, the graph's just going to look identical to the first interval from 0 to 2 pi. That means that it's periodic. So we're going to look at exactly what that definition is in a second. But most of the time when you're going to be asked to make a graph, you're going to be asked for 1 period. And 1 period means you're going to show me 5 key points. What are the key points? They're the blue ones that I highlighted, the quadrantial angles. And let me fill them in on the graph here. Here's a key point. Here's a key point. Here's a key point, here's a key point, last one. 1, 2, 3, 4, 5, that's 1 period from 0 to 2 pi. How far apart are each of these key points? They're pi/2 apart. So from 0 to the next key point to the next key point, they're all spaced out by pi/2. This means that the step is pi/2. Some books call that the increment. To get the step for any graph, you take the period and divide it by 4, and now we're going to talk exactly about what the period is. So notice that the graph repeats itself every 2 pi units. That means that the period is equal to 2 pi. So here's a definition, formal definition. We say a function f is periodic if there exists a positive real number k such that f of x equals f of x plus k for every x in the domain of f. The least such positive real number k, if it exists, is the period of f. This might be a lot for you if you're not used to reading math definitions. Don't sweat it. But basically it means that if at some constant, if you keep adding that constant to the input, to the x values, and the function value keeps popping up the same, then that means the graph's periodic. If it just repeats itself, okay? In regular terms, if the graph repeats itself. And whatever that constant is that you add to get back the same y value, that's the period, the least such positive constant. So in this case, the period's 2 pi. Don't put that definition on a note card and stress yourself out, okay? Now, the amplitude of sine or cosine is the absolute value of half the difference between the maximum and minimum y coordinates on the graph. So what that means for us is the amplitude here is equal to +1. Amplitude's never going to be negative. Okay, that's why it has this term here. We take the absolute value of half the difference between the max and min y coordinates. So we see that the max y value was +1, min y coordinate was -1, so half the difference between those is 1. Okay, now we have a theorem here. If n is any integer, then sine of x plus 2 pi n gives us back the original sine x, and then cosine of x plus 2 pi n gives us back cosine of x. All this is doing is confirming the fact that the period for sine and cosine is 2 pi. That's how long it takes for the graph to repeat itself or for the values to repeat themselves. That should make sense if you stop and think about it, because our unit circle, one revolution around it is 2 pi. So if you keep graphing beyond that, all you're doing is spinning around the unit circle over and over and over, and that's why the graph just keeps repeating every 2 pi over and over and over. Now, basically, the shape of y equals cosine x is the same as y equals sine x. It's just the 5 key points are a little different, okay? So let's go ahead and graph it. We're not going to make a table because we learned our unit circle, didn't we? Yes, we did. Here's the y-axis. Here is the x-axis. Okay. So we're only going to go up to 1, down to -1. The step is again pi over 2. So that's 1 pi over 2. 2 pi over 2 is pi. 3 pi over 2. And 4 pi over 2, we're back to 2 pi. You use 0 as one of your first ones. Okay, so what are the 5 key points? Imagine your unit circle. I will draw a quick one for you. Here's your unit circle. Isn't it lovely? Here's the y-axis. Here's the x-axis. At 0, the coordinate here is 1, 0. So the value of cosine of 0 is 1. So just remember, cosine's graph starts up on the y-axis at 0, 1. Then when we're at pi over 2, this point is 0, 1. So the x-coordinate matches the value of cosine, which is 0. When we're at pi, this is -1, 0. So cosine, the x-coordinate, is at -1. 3 pi over 2, this is 0, -1. And then at 2 pi, we're back up at the top. Okay? Now here, be careful. Here's the graph. I know that we didn't have to draw anymore, but if I did, say I put -pi over 2, it would go back to 0, right? So make sure this portion of the graph goes down if you don't include that extra point. Don't draw a deceptive arrow going upward. So this would drive me nuts. Don't do this, right? It doesn't go up. It goes back down after. Okay, so what's necessary? I did a little extra. You just need 1, 2, 3, 4, 5 key points. Again, amplitude is 1. That's the same. The period, 2 pi. 1 period is 2 pi. That's the same. 5 points. 5 points is 1 period. And then to get the step, you always take the period divided by 4. In this case, that's pi over 2. So for all your graphs, not just sine and cosine, if you need the step or increment, you take the period, divide by 4. Period for sine and cosine is both 2 pi. Okay. So same summary here. The graph of y equals cosine x never goes above 1 or below -1, and then it repeats itself every 2 pi units on the x-axis, crosses the x-axis at multiples of pi over 2. So if you'll see here, we have fancy schmancy computer generated graphs of sine x and cosine x with additional points. But like I said, you're only responsible for the 5 key ones. This is exactly 1 period graphed for each of them. I would mark points off though. I want some arrows here. You know what I mean? It's deceptive the way it looks. You would think it all ends, but it doesn't end. It keeps going. So even if you're asked for 1 period, please put arrows. Also, you're going to be asked to give the domain and range for each of these graphs. So let's go ahead and determine that now that we have the graphs completed in front of us. The domain, notice the graphs both extend forever to the left, forever to the right. So x values can be any real number. You can write that, or you can write it in interval notation from -infinity to infinity. Now the range, all the y values that the graph can take on, notice we said earlier that the graph was bounded between 1 and -1, right? The amplitude was 1. So that's going to correspond with the range. You always give it from least to greatest. So the smallest value the graph can take on is -1. I put a bracket in there because the graph actually achieves that y value. It's a point on the graph. It belongs to the range. And the largest value is +1. Okay, good. Now let's look at the graph of tangent x, okay? So some important things to remember about tangent. One being the period is equal to pi. that means the step, it's always the period divided by 4. So the step is only pi over 4. All right, interesting. Now, the graph of tangent includes vertical asymptotes. This is probably the first time you've graphed such a thing. So what is a vertical asymptote? It's a line that the graph approaches but never crosses or touches. This is a very loose definition, okay? And we're going to use that as the guide for our graph. It never crosses it or touches it. So I think the easiest way to figure out where these are going to be is remembering the fact that tangent of x is sine x divided by cosine of x. And so anytime cosine of x is equal to 0, that means tangent of x is undefined. And therefore, we're going to have a vertical asymptote. So vertical asymptotes occur at all x values where the function is undefined. Well, not all of them, as long as it's in lowest terms. You don't have to worry about that until you're in pre-calc, but I'm being picky because I don't want you to think every single point. Okay, so let's think about where tangent's graph would have vertical asymptotes. Basically, you're thinking to yourself, okay, it's going to have a vertical asymptote where it's undefined. That happens when the denominator is 0. So when is cosine equal to 0? Cosine is equal to 0 at pi over 2, and it repeats. So at pi over 2, 3 pi over 2, etc., etc. The values that we're going to use for the graph are at x equals positive pi over 2 and x equals negative pi over 2. Okay, so here we go. So pi over 2 and negative pi over 2 are where the vertical asymptotes are going to be on your tangent graph. And then remember we said the step was pi over 4, so I'm going to also fill in those x values here. When you have a vertical asymptote, you indicate that with the dashed line. So we have a dashed vertical line at pi over 2, dashed vertical line at negative pi over 2. Then the other values that you want to fill in are right here in front of us. So here's 1, 2, 3, 4, 5. So at negative pi over 4, think. So negative pi over 4, tangent there, that's in quadrant 4. It's going to be negative 1. So negative 1, we got to scale our y-axis. So say this is negative 1, this is positive 1. So it's going to be over here. Tangent of 0 is 0, and then tangent of pi over 4, we're back to quadrant 1, is positive 1. And here's the general shape of what tangent's graph looks like. This is one period. And so basically you only have 3 points, but each of the asymptotes counts as 4 and 5, like for our sine and cosine graph. So where are the points? What am I talking about? Here they are, 1, 2, 3, and then you include the 2 asymptotes. Okay, so key things to remember about tangent. The graph is only repeating every pi, not 2 pi, like sine and cosine, so the period's different. And then let's write out what the domain is. So the domain, we won't write in interval notation. It makes more sense to write it in set builder. So open up your set. It is all x's such that x does not equal, well, we have to remove all of the vertical asymptotes from the domain. So those occur, give the equation of where the first one is. The first one's at pi over 2 plus, how long does it take till another vertical asymptote pops up? Well, it's every period. Every pi, you're going to have another vertical asymptote. So how do you say that? Pi k, where k is an integer. Okay, this might be tricky. You'll get used to it because we're going to do it over and over. And then what about the range? Well, in this case, the graph goes up forever, it goes down forever, so the range is going to be from negative infinity to positive infinity. All right, very good. Now, if we're going to graph cotangent x, just a few things are a wee bit different. Remember, cotangent x is equal to cosine of x over sine of x. So biggest difference is that the vertical asymptotes are going to be in different places because the vertical asymptotes are wherever the denominator is 0, where it's undefined in this case. So let's think, when is sine equal to 0? At 0. So it's hard to see that there's a vertical asymptote right here on the y-axis. I usually draw a little extra above and below. And then the next vertical asymptote is going to be at pi. Here. Again, the period is pi for cotangent. The step is pi over 4. And let's fill in the vertical asymptotes. So here's another one at pi. And one period occurs between two vertical asymptotes, so you don't need to do any more than that, unless you're just feeling inspired and you like graphing and you want to keep it going. So here's pi over 2, pi over 4, and this is 3 pi over 4. And I'll just include 1 and negative 1. So let's think here. At pi over 4, positive pi over 4, cotangent is equal to positive 1. At pi over 2, cotangent is equal to 0. And at 3 pi over 4, it's negative 1. So notice it looks like the graph of tangent, except like it's been reflected over the x-axis. See how it's flipped? Tangent was increasing, cotangent is decreasing. And then the vertical asymptotes are at 0, pi, where would the next one be? 2 pi, 3 pi, etc. So let's list the domain and range now. The domain is going to be all x's such that x does not equal, well, remember I said give the equation of the first vertical asymptote. The first one is at x equals 0. The next one is at x equals pi. The next one would be at x equals 2 pi. So it looks like it's at x equals 0 plus an integer multiple of pi. But you can summarize that. You don't have to say 0 plus anything, right? 0 plus does nothing. You can just write pi k, where k is an integer. Okay, because it's impossible to sit there and list out all the equations of the asymptotes, right? They go on forever. What about the range? So same as tangent, it goes up forever, it goes down forever. So the range is from negative infinity to infinity. All right, nice. Now, for the graphs of secant and cosecant, we're just going to put those on pause. I'll show you what they look like once they're completed. And then when we get to a later section, we'll work on them in more detail from scratch together. But we don't need anyone's brain exploding today. All right, so here's a professional graph, computer generated. I'm already upset with it. Do you know why I'm upset with it? Yes, I mean, where are the arrows, right? So don't you dare do something like that. Arrows are a must. This is several periods, right? This is 5 periods being graphed. You only need to do 1. There's 1 period. The period is pi. Okay, and then here's the key points that we include. I'll highlight them for you. 1, 2, 3, plus the 2 asymptotes. There's tangent. Looks lovely. Here is cotangent. All right, same thing. You would just need these 3 points and then the 2 asymptotes. And then just for you to get a little sneak preview, the graph of secant x is shown here in red. Okay, it's based off of, since secant is equal to the reciprocal of cosine, we use the cosine graph and to give us like a building block, and then we'll graph secant using it. So cosine is shown in blue. That's not part of secant's graph. That's just used to build it. And then secant is there in red. Just some useful things for you guys to keep in mind about secant. The period is 2 pi also. Okay, so the step is going to be pi over 2. there is no amplitude for secant or tangent or cotangent or cosecant because they're not bounded. So we don't use amplitude to describe these graphs, only sine and cosine. And did I not have cosecant for you? It's very similar. Period 2 pi, step pi over 2. Okay, last thing, definition of even and odd functions. And this is something you're going to revisit again when you take pre-calculus. So we say a function is even if f of negative x is equal to f of x. And this corresponds with the function being symmetric with respect to the y-axis. A function is odd if f of negative x equals negative f of x. And this corresponds with the graph being symmetric with respect to the origin. Now, here's the theorem on even and odd trigonometric functions. You need to put this to memory. Cosine and secant are even functions. So what does that mean? That means cosine of negative x is equal to cosine of x. Same thing for secant. Do you believe it? I hope you do, but think about some number on the unit circle and it'll help you. For example, cosine of negative 30 degrees, what's that equal? It's rad 3 over 2, right? And that's the same as cosine of positive 30 degrees. It's also rad 3 over 2. So that's what an even function means. You change the sign of x that you're plugging into the function, but the y value is unaffected. The rest of the trig functions, sine, tangent, cotangent, cosecant, they're odd. What does that mean? That means that sine of negative x is equal to negative sine of x. Okay, so let's think about that one. Think about it. So sine of negative 30 degrees. What's sine of negative 30 degrees? You're in quadrant 4. It's negative 1/2. Now compare that to sine of positive 30 degrees. Sine of positive 30 degrees is positive 1/2. So this is what happens with an odd function. You change the sign of x that you're plugging in, and what's affected? The y value gets multiplied by a negative. Okay, that's an odd function. So the negative comes outside, basically. All right, so we're going to check whether the functions are even, odd, or neither using the definition. First things first, I'm going to introduce function notation. So I'm going to replace y with f of x. F of x equals x cosine x. So how do you check if a function is even, odd, or neither? You apply the definition, and you're going to replace x with negative x. That's all you do. And you clean it up and see what happens. So f of negative x, I'm replacing that x now with negative x times cosine of negative x. So look what happened. All of the x's got replaced with negative x. All right. And then let's see here. Let's simplify. So this negative x, nothing's going to happen. It stays negative x. And then since I know cosine is even, I can simplify that into just cosine of x. Okay, now let's compare what we have with the original function. Notice it's equal to negative x times cosine x, which is the opposite of my original function. And by definition, that means this is odd. Okay, so if when you clean up your function, look back at the definition. If f of negative x, right here, gives me the opposite of my original function, then it's odd. If f of negative x gives me the original, then it's even. If it doesn't fall into either of these categories, then it's neither. Let's do some more examples. I know this can be confusing if you've not seen it before. Okay, so let's introduce some function notation. So f of x is x plus sine x. And now let's go ahead and evaluate f of negative x. So f of negative x is going to be negative x plus sine of negative x. Now can I clean this up? Well, negative x, I can't do anything with it. But I know sine is odd, so I can rewrite this as minus sine of x, right? Remember, sine of negative x is equal to negative sine x, since it's odd. And I'm trying to compare this now to the original f of x. That's your goal. Is it the same? Is it the opposite? Or is it neither? Well, I can factor out this negative, and then I'm left with x plus sine x, which is actually what my original function was, right? X plus sine x, bam, there it is. So this is equal to the opposite of my original function. By definition, what does that make this? Yes, it's odd. Okay, couple more. Y equals x squared cosine x. So let's replace y with f of x. And then now we're going to apply the definition. So f of negative x equals negative x squared times cosine of negative x. Remember, I'm going to clean this up now. If I square negative x, the negative goes away because negative x times negative x is positive x. So this is x squared. Cosine's an even function, so cosine of negative x is just cosine of x. Okay, compare this with the original function. What do you notice? It's exactly the same. So f of negative x equals f of x. By definition, that means this function is even. Okay. Hopefully you're starting to kind of see how it works. Last one, y equals x squared plus sine x. So I'm going to change y to f of x equals x squared plus sine x. Again, I'm going to replace x with negative x. So this is going to be negative x squared plus sine of negative x. Make sure you guys, when you plug in negative x for x, and if it's raised to some power, you put the parentheses correctly. The parentheses go around negative x, and the exponent goes outside the parentheses. Don't mess that up because it will change the outcome when simplifying. Negative x squared, that's going to be positive x squared. And then since sine is odd, the negative comes outside, and now I have sine x. Okay, compare this to the original function. Is it the same? No, it's not the same, so I know it's not even. Is it the opposite of the original? Sometimes this is tricky for students to see. So the opposite of my original f of x would be if I took the whole thing and multiplied it by negative 1, which would mean I would get negative x squared minus sine x. Is that what I have here? Is that what I have right here? No, because the x squared isn't negative. So that means it's not odd, and we confirmed it wasn't even. So this one's neither. Neither, neither, whatever you fancy, okay? Now, if you feel like this is still a shaky topic, you're not alone. I have another video with more examples for my pre-calc class, but you're more than welcome. I'll link it right here if you just want to see testing for even, odd, neither, okay? Because it's just something that takes some practice. But it's going to be useful for the rest of your math career, trust me, not just with graphing, but later on when you start integrating in calculus. So you want to get this down, okay? Good. So those are just the basic graphs. When we move on in the next video, then we're going to start changing them up, okay, and giving them little transformations and makeovers. So stay tuned. That concludes this lesson, and we have lots of graphing to do.